Welcome to
radioactivity. So here we have a teacher use the equipment, shown in the diagram to measure the count rate at different distances from a radioactive source. So we have our Geiger-Müller tube here, we have our scaler here, which is called a counter, we have our source, and we have a means of measuring our distance between the Geiger-Müller tube and the source. Her results are shown in table 1. So we have distances ranging from 0.4 to 2.0 meters. We have count rates ranging from 143 to 18. We notice that we have 3 lots of 18 here. As the distance increases from 1.6 to 2 meters, the count rate is not changing. We have a corrected count rate, and so we are hopefully remembering what we mean by corrected count rate. This is the count rate less the background count. But if we didn't remember that, we'd be seeing the corrected count rate here is 0. So clearly these figures are the count rate minus 18. So that should give us a clue if we've forgotten what corrected count rate is. So we have corrected count rate, and distance. What is the value of the background count rate? Well, we've established that it is 18 counts per minute. And we're also perhaps remembering that counts per minute is not the SI unit, it'll be counts per second, becquerels, that's the activity. So what information does the corrected count rate give? Well, that is the activity, perhaps, or the count rate, which is due to the source alone. There's no component of background radiation with the corrected count rate. The radioactive source used in the demonstration emits only one type of radiation. It is not an alpha emitter. How can you tell from the data in the table? So if it was alpha, what would be happening? Well, if it was alpha, then with a few centimeters distance, possibly even at this distance, 40 centimeters, certainly 40 centimeters, this would be the background count. So because there is a count at 40 centimeters, and because that count due to the source, the corrected count, continues to 1.4 meters, it can't be alpha because the range of alpha is a few centimeters in air. So how do we say that then? There is radioactivity detected beyond a few centimeters from the source, and alpha has a range of a few centimeters in air. So it can't be alpha because whatever this radiation is traveling a lot further than a few centimeters. Well, the graph of corrected count rate against distance for distances between 0.4 and 1.4 meters. Let me just make my line a bit thinner now. So we've got 0.4, 125, 0.4, 120, 122, 124, 125 would be there. It's a little difficult to see on there. So there's 125. Because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares to 20 counts per minute. So each square would be 2 counts per minute. So we've got 20, 120, 122, 124, 125 would be there. If we then look at our second one, 0.6 and 56. So 0.6, 20, 40, 42, 44, 46, 48, 50, 52, 54, 56 is there. And the next one, we have 0.8 and 31. 0.8 and 20, 22, 24, 26, 28, 30, 31 would be there. Remembering that you have to plot these within half a small square tolerance. Your examiner will allow you half a small square, plus or minus. So that was 0.8. 1 is 20. 1, 20. That was easy. 1.2 is 14. 1.2, 2, 4, 6, 8, 10, 12, 14. Uh, 1.4 is 10, and that's where we're asked to stop. 2, 4, 6, 8, 10. So there we have our points plotted. Now, it asks us to plot the graph. There are 3 marks for this. So there will be 2 marks for the plotting and 1 mark for our nice smooth curve through the points, which, given that I'm doing this on a screen, will not be so smooth. But what we need is a smooth curve going through our points. What we don't want is to go dot to dot. It should be a smooth curve. Okay, so there we have our graph for 3 marks. The half distance is the distance a detector has to be moved away from a radioactive source for the corrected count rate to halve. The student has the hypothesis a radioactive source has a constant half distance. Table 1 is repeated for your information. Use table 1 to determine if the hypothesis is correct. So our count rate then, in halving it, let's have a look for some nice easy numbers. There's 10 to 20, or 20 to 10. 31 to 14 is almost half. So 31 to 14, the distance is 0.4. That distance is 0.4. 20 to 10 is 1 to 1.4. That is also 0.4. That'll be 112. So that's not. So it looks like we have a constant half distance, doesn't it? 31 to 14, 20 to 10 looks like a constant half distance. We would say, yes, the hypothesis is correct, because from 31 to 14, which is approximately half of 31, we have a distance of 0.4 meters. Going from 20 to 10, which is times 0.5, we have a distance of 0.4 meters. We'd like a third calculation if we could, but our data doesn't really allow for that. So if you went from 125 to 63 to about 32, that'll be 2 half distances. You'd expect that to be 0.8. But that, you see, 125 to there, is 0.4. But (125) to 31 is approximately 2 half distances. But it's actually 0.4. So no. So I would say no, because although those two seem to fit, if we did 125 to 31, which is basically two half distances, it doesn't, because that's also 0.4. So no. Teacher places a beta source and a detector in a magnetic field. The arrangement of the magnetic field is shown. Beta source, detector, field along the direction of travel of the beta particles. And here we are at right angles to the direction of the beta particles. We have a set of results. Describe and explain the effect of the magnetic field on the count rate detected by the detector. So, fixed distance, the count rate without the field is 48. The count rate with the field in experiment 1, where the field is in the same direction as the direction of the beta particles, no change. And here we have less beta radiation arriving at the detector than we had before. So again, for 2 marks, I would say in experiment 1, no effect. In experiment 2, the magnetic field, the B field, deflects the beta particles. So fewer arrive at the detector. The experiment is repeated with a different distance from the source and the detector. It's a bigger distance this time. We have the repeated results, 19, 18, 20. Now, the thing to remember is that this is all part of the same question. So this 18 rings a bell with me. If we go back up here, we see that our background count was 18. This is the same experiment, basically. So you have this teacher conducting an experiment. You have the teacher conducting, or a student conducting with the teacher, another experiment on the half distance. This is the same data, remember. And then we have a teacher placing a beta source and a detector in a magnetic field. So we have the results are approximately equal to the background count. So the distance is too great for beta to arrive at the detector. The variation, because you've got 19, 18, and 20, well, that's down to the randomness. Oops. Of decay. This is just random variation in the background count, this 19, 18, 20. So I think if you didn't realize that this is the same experiment and so it has the same background count, you might struggle to answer this. But the magnetic field is having no effect at all because the count really isn't changing. The variation in the count is due to the natural variation, the randomness of radioactive decay. So a question has asked us to demonstrate our understanding of background count and corrected count. It has asked us to demonstrate our knowledge of the properties of alpha, which should go along with the knowledge of beta and gamma as well, their properties. It has asked us to plot a graph, which you will always be asked to do at some point. It has asked us to analyze some data and to use that analysis to come to a conclusion. So initially we thought, well, this is looking pretty good. We have this fairly good fixed distance for half the count, but then we look up here and actually it doesn't work. So that's why there's 3 marks for this. You need to try to find 3 pieces of data or 3 pairs of data points to acquire these 3 marks. And on this one, there are only really 2 obvious ones. The third one is harder to see, but is essential for that 3rd mark. Then we've looked at the effect of magnetic fields on beta. You should recall that it doesn't affect gamma at all because gamma has no charge and magnetic fields only affect moving charge. And the field has to be at right angles to the direction of motion of the particles. So there it is. And then finally, of course, there was that bigger distance outside the range of beta. And so the readings were reduced to the background count.